Hello everyone. We want to look at this was question on gravitational fields. It was actually on satellites. The question appeared in November 2022. Actually, the paper was done on the 8th of December. So it reads, the period of rotation of planet Earth is 24 hours. Calculate the distance of a satellite above the Earth's surface when it is put in a parking orbit. So that satellite would be called a geostationary satellite. So if you look at this, the first thing we will look at is how to find the velocity and then the period or the revolutionary period of a satellite. First, what we have to know is consider a satellite that is revolving around a planet. So if we consider this as a planet, and this is the satellite that is revolving around the planet. The planet has a particular mass, big mass, and then the satellite has a small mass. There are two forces that keep this satellite into position. One is the force of attraction between the centers of the masses, that is Newton's force, F equals to G times the mass of the planet times the mass of the satellite all over r squared, where r represents the distance between the satellite and the planet. But there is also another force that keeps this object. We assume the satellite takes a circular orbit. Then also the force which is going to be the centripetal force. The centripetal force is going to be the force that keeps this object in a circular path, and that is going to be mv squared all over r. Now, if we consider this satellite taking this path, then we're going to say these two forces are equal. So it means we're going to have g times the mass of the planet times the mass of the satellite all over the radius, that's the square of the distance between them, is also going to be equals to mv squared all over r. So one thing we can do is we have m on both numerators, and then we also have r on both denominators. So we can multiply each side by r over m, multiplied by r over m, so that the m will reduce and then the r will also do. So the r will cancel on the right and then the m will reduce. Then what we're going to have is the velocity squared, which is the speed, is going to be equals to gm all over r. In other words, v will be equals to square root of gm all over r. But we know from gravitational field, that is gravitational field strength, which is gr squared is going to be equals to g times m from gravitational field strength. In other words, what we are going to say is the velocity therefore is going to be equals to root of, in the place of gm we put gr squared and then divided by this r, hence velocity equals to root of g times r. This is the velocity of a satellite on its orbit. That is one thing we can do. But if we come back to the upper one here, that is this expression, we said velocity of a satellite on its orbit. The velocity of a satellite, therefore, we can say v is equals to 2 pi r all over the period. That is when we consider a satellite on its parking orbit. A satellite is said to be on its parking orbit if it is at a particular position, whilst the planet Earth, or the planet in general, revolves or rotates about its axis. So in this case, we're going to have, so we already get the velocity. We want to have a formula for the revolutionary what? Revolutionary period. So if we look at this, then we will have in the place of v squared here, that is in this expression, in the place of v squared, we are going to substitute what? 2 pi r over t. So we're going to have 2 pi r all over t. All these things squared will be equals to g times m all over r. Now remember, our target is to know the revolutionary what? The revolutionary period. So it means we will have 4, 2 squared is 4, pi squared r squared over t squared will be equals to gm all over r. When we cross multiply, we will have t squared gm will be equals to 4 pi squared. Now this is r squared and that is r. When we multiply the two, we are going to have r to the power 3. So in simple terms, we would divide both sides by, remember, capital G is gravitational field constant and capital M is mass of the planet. So this guy would cancel with that other one. So we have t squared is equal to 4 pi squared r cubed all over gm. And this will match Kepler's start law. You know, Kepler's start law says the square of the period is directly proportional to the cube of the radius of the semi-major axis, or the revolutionary radius, as the distance from the center here. In this case, remember, our target was to know the velocity and also the period of revolution of a satellite. So when we look at this now, we obtain an expression for the velocity and the speed and the revolutionary period. To remind you, you see that is the big planet and this is the satellite. Remember, if we are talking about the Earth now, then it means this distance will be radius of the earth, and then this distance will be some height above the surface of the earth, let's say h. So in our next video we will show you a WASP question and how to answer that WASP question using this information. Thank you for watching that.